Hello everyone, this is Ghanashri. Today I'll be talking about the experiment data that's used in a paper that tries to say that the greedy hill climbing approximation algorithm outperforms every other algorithm whenever we are trying to maximize the reach. And in this case, the paper says that this algorithm will yield the highest results. That is about 63% of the times it performs really well in case of selecting the nodes such that the reach is always maximized. And in order to test this scenario and prove, we will need two performance models. And for this purpose, we are considering linear threshold model and independent cascade model. This is the premise of the problem. And assuming that that is understood, I'll be talking about the experiment data that is used to verify these results. And it's important that we choose a data which will effectively capture the workings of an underlying social network. And for that purpose, we have considered a combined list of papers from the high energy physics theory section that are co-authored. And with this data, we have constructed a finite directed collaborative graph. Each node in that graph will represent a researcher. Connecting edges will represent the paper that they have co-authored together. This way, the resulting graph had about 10,748 nodes, aka that many researchers, and 53,000 distinct edges, meaning that many distinct papers that they have co-authored together. Once this data is considered, we will run this data for both the performing model using greedy hill climbing algorithm. Both of the models, that is the linear threshold model and independent cascade model, will have certain weights assigned to their edges. In case of linear threshold model, we will choose these weights based on the uniform distribution between 0 and 1. And in case of independent cascade model, we will assign the weight to these edges by a probability event, like for example, flipping a coin. And once the weights are assigned, we will simulate this process. We run the simulation for about 10,000 times, each time choosing a different threshold to ensure that the algorithm performs at least 63% of the times better than the other heuristics in all of the cases. In each case, the algorithm has to outperform the other algorithms. So it's important that whenever we are trying to prove the performance of one algorithm, we actually compare it with certain other algorithms and have a good understanding of those algorithms as well. In this case, the other three heuristics that we're comparing our algorithm with are degree centrality algorithm, distance centrality algorithm, and random nodes. In case of degree centrality algorithm, we will select the nodes based on multiplicity. Like whichever node is having highest multiplicity, we will choose those nodes. And in case of distance centrality algorithm, we will choose the node with shortest path of activation. And in case of random nodes, we will choose the nodes obviously in random, as the name suggests. But the drawback with these degree centrality and distance centrality algorithms could be that we can end up choosing two different nodes which will have the same path of activation. Like they can end up activating the same set of nodes, which will not result in maximizing the reach, which is the end goal of our paper. Like if I have to explain this in a real-time example, let's say you want to market certain textbooks, and who would you choose? You would choose teachers whoever is having maximum class strength to use those textbooks to market your product. But the drawback here could be you can end up choosing two different teachers who will teach the same exact class. Even though the class strength is larger, both the teachers will be end up influencing the same set of students, which is not the goal of our paper. We need to maximize the reach, not influencing the same set of people two, three times over. That is one of the major drawback of degree centrality and distance centrality algorithm. So when we run this simulation and plot the results, we can clearly see this distinction in our plotted graph. This first lines is the greedy hill climbing algorithm performance. Second one is the degree central one. Third is the distance central one, and obviously last one is the random node selection. Our GHA algorithm outperforms the degree one by 18% and outperforms the distance centrality algorithm by 40%. And obviously, the random choosing of nodes performs the least of all of the other algorithms. And the resulting graph is similar for both linear threshold model and independent cascade model. We can see similar results in both of the cases. And so the takeaway for us from this paper was that by combining linear threshold model and independent cascade model, that is considering not just the structural aspects of a graph, but also the dynamic aspects of the graph, we can implement a broader framework which can effectively handle the non-progressive process as well. What is non-progressive process? Here we assume that the nodes can only go from deactivated state to activated state, but there can be edge case scenarios where a node can go from activated state to deactivated state as well. That can be effectively handled if we consider the dynamic aspects of a graph, and it can eventually result in more realistic marketing, and that can yield perform highest results and yield maximum results by reaching maximum number of people. So which is the end goal of our which is the end goal of any algorithm. So that can be effectively uh, uh, reached by considering dynamic aspects of a problem. Yeah, thank you.
Hi, this is Suharsh. Today I'll be taking you through aspect-oriented programming, and we'll also see how this is implemented in Spring. So before we start talking about aspect-oriented programming, let me also take you through what a cross-cutting concern is. So basically, when you write an application code, you tend to mix your business logic with a lot of other things. Say, suppose you have a code where you want to validate user inputs, or you want to check some security related aspects. For example, you have to authenticate the user, and then you'll have some code related to logging. So you tend to mix all these code together along with your business logic, which will result in your code becoming messy, because you have mixed up your business logic with the code related to security, the validation, and the logging. So aspect-oriented programming talks about how you can basically separate out these concerns. So you separate out validation, you separate out security, you separate out the transactions, you separate out the logic, and you keep your business logic clean. So it's basically provides an abstraction for all these concerns. So the security, validation, and all these different types of code that you tend to mix, these can be called as a concern. So these are basically concerns. So aspect-oriented programming basically helps us in providing, or hiding or separating out these concerns from the core business logic. And aspect-oriented programming is basically the programming paradigm which helps us to encapsulate these concerns so as to have a very modular code. So in this way, it helps us in reducing the tangling and scattering, in other words. Now, like I said before, it clearly helps us in separating out the concerns. So we're just keeping the business logic as one concrete thing, and then we separate everything out, related to validation, authorization, everything into a separate entities or aspects. Now it is basically a good implementation of the KISS principle, which is basically about keeping the code simple, stupid, straightforward, and strong. So now these are some of the keywords that we have to review when we have to talk about AOP, especially when we are going to cover the topics in Spring. So we have something called aspects. So aspects are basically abstraction of a concern. So by that, I mean the aspect can be anything like a validation aspect, which will handle all the validation of the user inputs, handle all the validation of the data that you get in. And then there can be a security aspect, which will deal with ensuring that the user is an authenticated user, the user has the required authorization. And then you can have something like a logging aspect, which will take care of logging your which will take care of ensuring that everything is logged. so that you record everything whatever is happening in the code. So you can have several such aspects. Now you have something called advice. Advice is basically a code that implements that concern. So basically by that I mean advice is basically the code, the we said, right, we separate out the validation, the security aspects from the business logic. So we have to put this somewhere. So we put you have to put this code somewhere, right? So the validation has to be called before your current method which contains the business logic is executed. So we separate out this logic related to the validation and security, etc., into something called as an advice. So this is basically an advice is basically an actual implementation of a concern. And then join point is nothing but a point in the flow of program execution. So you have a method which constitutes your business logic. Now your concern has to be implemented separately. So let's take the case of a validation concern. So you implement that validation concern, in which you implement basically you're validating, let's say we are validating the user inputs. So we'll have a separate method, and we call that advice. The advice is the method which implements the validation of the user input. Now this validation advice has to be called before your business logic method is called, so that before the invocation of your business logic method, that is basically a join point. Now you have point cuts. Point cuts is basically a collection of join points. So it's usually generally expressed as predicates or a regular expression which would qualify several methods, which will basically qualify several methods after or before which our after or before which our advice has to be called.
Hello, Professor. My name is Abhishek, and today I'll talk about cloud computing. So I'll discuss a couple of important topics in cloud, such as the benefits, the definition, and the type of deployment models we have, or as-a-service models, and also the uses of cloud computing. First, we'll start with the definition itself. So cloud computing is the on-demand delivery of IT resources over the internet with pay-as-you-go pricing. So instead of buying, owning, and maintaining physical data centers and servers, we can access technology services such as computing, power, storage, and databases on as need basis. So just to simply put it in simple terms, cloud computing is a delivery of computing services including server storage, databases, networking, software, analytics, and intelligence over the internet to offer faster innovation, flexible resources, and economies of scale. You typically pay only for what cloud services we use, helping us lower our operating costs, run our infrastructure more efficiently, and scale as our business needs change. So even more, I would like to talk about one more definition from National Institute of Science and Technology. So cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned, maintained, and released with minimal management effort. This cloud model is composed of five essential characteristics, three service models, and four deployment models. So further, I'll talk about such models. The other benefit we have is productivity, which means on-site data centers typically require a lot of racking and stacking, hardware setup, software patching, other time-consuming IT management chores. Cloud computing removes the need for many of these tasks, so IT teams can spend time on achieving more important business goals. So these are the benefits of cloud. Next, we'll talk about the types of cloud computing. Now we'll talk about the types of cloud computing models. First, we have infrastructure as a service, which means IaaS contains the basic building blocks of IT, like the server storage, physical capacities, and all such things. And contains the basic building blocks of IT, typically provides access to networking features, compute and data storage space, IaaS provides you with the highest level of flexibility and management control over IT resources, and is the most similar to existing IT resources that many IT departments and developers are familiar with today. And we have secondly platform as a service. Uh, PaaS removes the need for us to manage underlying infrastructure, usually hardware and operating system, and allows us to focus on deployment and management of our applications. This helps us to be more efficient, as we don't have to be worried about resource procurement, capacity planning, software maintenance, patching, or any other of undifferentiated heavy lifting involved in running our application. Thirdly, we have software as a service. It provides a complete product that is run and managed by service provider. In most cases, people referring it to SaaS or end user applications. With the SaaS offering, we don't have to think about how service is maintained or how underlying infrastructure is managed. So you'll need to think about how you will use that particular piece of software. A common example of SaaS application is a web-based email where you can send and receive email without having to manage features addition to the email product or maintaining the server's operating system that the email program is running on. We have next we'll talk about the cloud deployment models. I'll talk about the cloud deployment models where we have public cloud, which means a cloud-based application is fully deployed in the cloud, and all parts of the applications are running in the cloud, which are owned and operated by third-party cloud service providers such as Azure or AWS, which deliver computing resources like server storage over the internet. With a public cloud, all hardware, software, and other supporting infrastructure is owned and managed by the cloud provider. You access these services and manage your account using a web browser. Next, we have hybrid cloud, which combine public and private clouds bound together by technology that allows data and applications to move between private and public clouds. A hybrid cloud gives you your business greater flexibility, more deployment options, and helps optimize your existing infrastructure, security, and compliance. And later we have a private cloud, or we can say on-premise cloud. So this is deploying resources on premises using virtualization, so resource management. A private cloud can be physically located on the company's on-site data center. Some companies also pay third-party service providers to host the private cloud. A private cloud is one which the service infrastructure are maintained on a private network. So that is it for the presentation. Thanks.
Hello, Professor, and hi everyone. I'm Lakshmi Gundlapalli, and today I'm going to talk about distributed systems. Though this architecture came up some 50 years back, it evolved over time from then, and most software designs today are based on this type of architecture. So in this presentation, we'll see what a distributed system is, what are the examples, what are the important features and advantages and disadvantages of distributed systems. So distributed systems are also called as distributed computing. It is a collection of independent components that are located on various different machines that can communicate with one another, and they achieve a common goal like serving a web application or a database. The major goal is to prevent failures, that is to make the system available as much as possible even when one of the machines fails. The other important features of a distributed system include resource sharing. Here, the hardware, software, or any kind of data that can be shared between the machines. The next feature is openness. The software to be designed should be as open as possible. The third important feature is concurrency. Same machine can handle multiple requests, or multiple machines can handle same function at the same time. Fourth important feature is scalability. The biggest advantage we have with distributed system is scalability, and we can expand the systems horizontally here. Fifth important feature is fault tolerance. It's a measure to identify and fix the failures as soon as possible. Sixth important feature is transparency. This tells about the amount of transparency that various nodes or machines in a distributed system maintain. Let's look at some of the examples of distributed systems. The examples start from 1970s itself, when we have this distributed networks initially. LANs or peer-to-peer networks all enable communication between various machines, thus forming a distributed network. Then we have telecommunication networks. Mobile or cellular networks are distributed networks where the base stations are distributed in different areas, forming a distributed network. Some more examples include distributed real-time systems, parallel processing, distributed artificial intelligence, distributed database systems. Coming to the architecture part, the main concern when designing a distributed system is we need to have a proper network that connects all the components, whether it is software, hardware, or even machines together for transferring machines from one system to the other. When it comes to the hardware part, we can use IP address or cables to connect one machine to the other. For the data part, databases or objects or even files are shared between machines. Reliable communication or how a node retries when there is a failure are important features that need to be considered when designing a distributed system. We have various architectures that are developed over years for distributed systems. Let's see one by one. The first one is the client-server architecture. Here we have a single server and there are multiple clients. Examples include the printer and the database or web servers. They have multiple clients and they share the data with the server machines. Next, we have three-tier architecture. Here we have three layers, the client, the middle layer, and the server side. The client is not intelligent here, and it relies mostly on middle tier to do processing and decision making. Middle tier receives requests from clients, processes the data, and then forwards it on to the servers. Next, we have multi-tier architecture. Here we have a server, multiple data tiers, and presentation tiers. There is an application server that contains business logic and interacts both with the data tier and the presentation tier. Then we have peer-to-peer networks. Here there is no centralized or special machines that does all the work. All the responsibilities are split up amongst the machines involved and each could take on the role of a client or a server. Coming to the advantages and disadvantages of distributed systems, they are mainly useful for scalability, high performance, and high availability. Coming to the first important advantage, they provide unlimited horizontal scaling. Whenever there is a requirement to scale machines, they can be added easily. The second important advantage is latency. Latency is low in distributed systems as machines are geographically located closer to the users. It reduces the time taken to serve the users. Another important advantage is fault tolerance. If one server or data center goes down, others could serve the users. Coming to the disadvantages or the challenges that need to be taken care when we are designing a distributed system, the first concern is data integration and consistency. We need to synchronize the data and states of machines in a distributed system, and it's very challenging when nodes are starting, stopping, or they are failing to maintain the proper synchronization between the various nodes. The second important challenge is network and communication failure. Sometimes messages may not be delivered to right nodes or they are delivered in incorrect order, which can lead to breakdown in communication and functionality. Third important concern is management overhead. More intelligence, monitoring, logging, load balancing functions need to be added for visibility when there is a failure in a distributed system, because it is difficult to identify which node has failed amongst all the nodes. So it requires more logging and monitoring. So this is all about distributed systems overall introduction. That's it for today. Thank you.